Hello, today we will continue with chapter 5, which is work and energy. We will work a little bit on the work concept in the beginning, and then we will introduce a new theorem that we will be applying, and that's work energy theorem or work kinetic energy theorem. And we will do exercising on it. So just a quick reminder, work done by a force is Fx times delta x, and the unit of work is joules. Okay, let's look again at this exercise. It's similar to exercise 1, page 36. The only difference that here we introduced friction. Okay, so a man pulls a sled loaded with salmon. The total mass of the sled and salmon is 50 kilograms. And the man exerts a force of magnitude 120 Newton on the sled by pulling on the rope. See the adjacent figure. Assume that the coefficient of kinetic friction between the loaded sled and the snow is 0.2. So this is the difference here, that now we have this coefficient of kinetic friction. So let's write the given. We have mass equal 50 kilograms. We have the force equal 120 Newton, and we have this mu equal to 0.2. Calculate the work, the net work done on the sled if the rope is horizontal to the ground, that is, if theta is equal to 0, and he pulls a distance of, so delta x is equal to 5 meters. Okay, so this is the sled, and these are the new forces acting on it. So there is the F, there is the normal, there is the friction, and there is the weight. So it's asking for W net. So if it's asking for W net is equal to work done by all these forces, by W. So let's say work done by friction plus work done by W plus work done by normal plus work done by this external F. Okay, so this is W net. Now we know what is the work done by friction. I come to the friction. It is the friction, the x component of the friction times the distance delta x. Okay, what is the x component of the friction? It is minus, because it is the whole thing, but in the opposite direction. So it's minus F times delta x. Okay, what's the work done by W? It is Wx delta x, but W is all on the y-axis, so it doesn't have any x component. So it is 0. Similarly, the work done by normal, because it's all on the y-axis, it doesn't have an x component. Okay, so this is the work here. It is the force times the x component of the force times delta x. Plus, what's the work done by this F over here? It is Fx delta x, which is the whole of F, plus, because it's in the positive, along the positive x-axis, times delta x. Okay, now we want to solve this. What is the rule for friction? Friction, it's not giving me what is the friction, it's giving me mu. So in the given I have mu, so I have to use minus C mu times N. This we have to remember from Newton's, from the forces chapter. Times delta x, so times 5, plus F, which is 120, times 5. Okay, now I have to calculate N. What do we use? Always to calculate N, we always use summation of Fy is equal to 0 from Newton's second law. Okay, so summation of Fy is equal to 0. That is, what do we have on the y-axis? I have N. So I have Ny plus Fy plus Wy plus Fy is equal to 0. Fy and Fy disappear because they are all on the x-axis. So I'm left with n minus w equal to 0, which means n is equal to w, which is m times g. Okay, so I come now to my w net, and I come to w net. So W net is equal to minus mu. Mu is 0.2 times N, which is M times G. M is 50 times G is 10 times delta X, which is 5, right? Plus 120 times 5. I do the calculation. This will give me 100 joules. Okay, so if I have several forces acting on an object, then to get W net, it is simply the work done by the first force plus the work done by the second force plus the work, as much as forces I have. If I have 10 forces, then here I will have 10 components. Some of them will disappear, some of them will remain. So I need to know how to calculate W net. Now, why we are learning how to calculate W net? Because over here you find the solution. Because we will come to an important theorem, which is work energy theorem. Over here, I'm deriving the theorem, but you don't need to know how we derive it. You just have to memorize the result. But let's derive it together. So let's take an object of mass m, and I apply F naught on it to move it a distance of delta x. Let's say that in the beginning, the initial was 0, and as it is moving, it is having a velocity v. Okay, so there is v final equal v along the way. What do I know about W net? From the formula, W net will be F net times delta x. This is what I did in the previous exercise, right? I put all the forces times delta x. So W net is F net times delta x. What do I know from Newton's second law? I know that F net is ma, right? This is in Newton's second law. F net is equal to ma. So I have now W net is equal to ma delta x. What do I know from the first chapter? From the first chapter, which is on kinematics, I know that V final square is equal to V initial square plus 2a delta x. From this formula, if I take a delta x to the other side, I will have a delta x is equal to v square minus v initial square divided by 2. Okay, so if I keep a delta x here, I take v initial square the other side, a delta x will be v square minus v initial square divided by 2. Now, back to W net. So W net is ma delta x. Instead of a delta x, I will put v square minus v initial square over 2. So this is here instead of a delta x. And now let's look at it. W net is equal to m times v square over 2 is half mv square. M times v initial square over 2 minus, so this will be minus half mv initial square. And this is nothing but kinetic energy final minus kinetic energy initial. And this is work energy theorem that says W net is equal to delta kinetic energy. So W net is the change in kinetic energy. It's kinetic energy final minus kinetic energy initial. When do I use this formula? I use this formula mostly if there is a friction, okay? Because if there is friction, I cannot use conservation of mechanical energy. I cannot use mechanical energy final equal mechanical energy initial. So when I have friction, I need to use W net equal delta kinetic energy. Let's solve some exercises using this formula. So now over here, I'm reminding you that we have W by any force, it's Fx delta x, and W net is delta kinetic energy. Let's do the first exercise. So A hockey puck has an initial speed of 5 meters per second. So let's write. So this is the initial is 5 meters per second. The coefficient of kinetic friction, so mu, is equal to 0.05. Okay. The first part, is the mechanical energy conserved? I have to remember, mechanical energy is conserved if there is no friction. But in this exercise, they're giving me there is coefficient of kinetic friction. So mu is not 0, or friction is not 0, implies mechanical energy is not conserved. Okay. So done with this part. Part B. Determine the distance delta x. How much is delta x covered by the puck before coming to stop? What does it mean coming to stop? What does it mean to stop? It means V final is equal to 0. Okay, so here I have friction, I have the initial, I have the final, and I want to calculate delta x. In this exercise, you just remember in this lesson, so far we know mechanical energy is conserved or work energy theorem. Since mechanical energy is not conserved, so we have to use work energy theorem. That says what? Let's do it over here. W net is equal to kinetic energy final minus kinetic energy initial. Okay, so now in order to define what is W net, I have to find the forces first. So let's draw. This is our object, and we will put all this is a hockey puck, you know, where we play hockey. So it is a horizontal surface. It is a horizontal surface. And the forces acting on it, the forces acting on this object will be the weight, the normal, and friction. They didn't say there is any other force. So these are the only forces I have. So this is normal. This is W. And this is friction. These are forces. Okay. So the friction is, the object is moving to the front. That's why the friction is to the back. So the x-axis is to the front. Okay, the object is moving to the front. So this is x-axis, this is y-axis. This is y-axis. Now, which forces contribute to W net? Similar to the previous exercise, there is no NX, there is no WX. So the only force that will contribute to W net is the friction. So I will have minus F times delta X is equal to kinetic energy final is half mv final square minus half mv initial square. Okay. Now, friction, they give me mu, so I will do exactly like I did in the previous exercise. So mu times n times delta x is equal to, what is V final? It is 0. So this is gone. So I will be left with minus half mv initial square. Okay, to get n, to get N implies summation of Fy is equal to 0, just like I did before in the previous exercise. And I will get Ny plus friction Y plus Wy equal to 0. But friction Y is 0 because it's on the x-axis. So I will get N plus N minus W is equal to 0. So N equal to W equal M times G. I go back to my equation. Minus mu times N, which is M times G times delta X is equal to minus half mv initial square. Okay, now I don't have M, but both sides contain M, so I can divide by M. So this M and this M disappear. Okay, there is minus here, they disappear. Okay, now let's put what I have. Mu is 0.05, so 0.05 times G, which is 10, times delta X is equal to half V initial square. V initial is 5 square. So if I solve this, I will get 0.5 delta X is equal to 25 over 2, which is 12.5. So I will get delta X is equal to 12.5 divided by 0.5. And this is nothing but 25. Okay. Let's do a similar exercise. Okay, so this is the solution. So this is an exercise similar to the one on page 35, number 10, because in the booklet, it's not written properly. So I found a similar exercise. So a skier starts from rest. So what do I know? It starts from rest. So at point A, V initial is equal to 0, implies kinetic energy is equal to 0, right? Okay. At the top of a frictionless incline of height 20. So there is H equal 20, implies there is a GPE equal mgh. Okay. So at A, what is mechanical energy? Since it's frictionless, so here I can use M mechanical energy at A. Let's write it this way. It's equal to mgh of A. Okay. This is at A. This is frictionless, so I can use conservation of mechanical energy. At the bottom of the incline, so at point B, okay, the skier encounters a horizontal surface where the coefficient of kinetic friction between the ski and the snow is 0.2. So from B to C, there is friction. So I cannot apply conservation of mechanical energy between B and C. I can only do it between A and B. Okay, they give me the mu to be 0.210. Okay. Find the skier's speed at the bottom. So we need to find the speed at point B. So at A, I have V initial 0, kinetic energy is 0. I have H, so mechanical energy is mgh. At B, what do I have? At B, I'm at the bottom, so H is equal to 0. So there is no GP, but there is VB, implies there is kinetic energy, which is half mvb square. Okay, so mechanical energy at B is equal half mvb square. Okay, this is the information at B. So let's start. Find the scalar speed at B. So to solve this, I will say between A and B, no friction implies mechanical energy is conserved. So mechanical energy at A is equal mechanical energy at B. Mechanical energy at A is mgh of A is equal to mechanical energy at B, which is half mvb square. Okay, m is not given, but I can divide by it because it exists on the both sides of the formula. Okay, now I just solve for this. G is 10 times the altitude h is 20 is equal to half vb square. So 200 equal half vb square. So vb square is equal to 200 times 2, which is 400. So vb is the square root of 400, which is 20 meter per second. Okay. Now, how far does the sphere travel on the horizontal surface that is between B and C? So part B, how far, it means delta x. So delta x equal how much between B and C before coming to rest. So I have VC is equal to 0. So here I have VB from the previous part is equal 20, and this is V initial, right? And I have VC equal to 0, which is V final. And I want to calculate delta x. So here there is a friction between B and C, so we have to use work energy. So W net. So use work energy theorem. W net is equal to delta kinetic energy or kinetic energy final minus kinetic energy initial. W net, what are the forces between B and C? Let's draw our object. So this is the guy. What are the forces acting on him? There is a friction, there is normal, there is weight, right? And he is moving to the right. So the x-axis is to the right. The y-axis is perpendicular to it. Okay. This is normal here. This is weight here. And there is friction here. So what forces contribute to the work? Only the friction. So what forces contribute to W net? Only the friction. W net, so it is Fx delta x plus Nx delta x plus Wx delta x. It's equal to half mv final square minus half, which is Vc in this case, minus half mvb square. Okay, few items will disappear here. So nx is 0 because it's on the y-axis. Wx is 0 because it's on the y-axis. Vc is 0 because it stops here. So I'm left with fx is minus f. So minus f delta x is equal to minus half v m v b squared, sorry, mvb squared. How to calculate f? It is minus mu because they're giving me mu times n, and this is similar to the previous exercise, so no need to do it again, times mg, okay, times delta x is equal to minus half m vb squared. M and m that cancel out each other. Okay, so there is here m, there is here m, they cancel each other. Now, mu is minus, sorry, minus and minus also cancel each other. So 0.210 times g, which is 10, times delta x, which is my unknown, is equal to half VB squared, which is 20 squared, which is 400. Okay, so I get 2.1 delta x is equal to 200. So delta x is equal to 200 divided by 2.1, which is equal to 95.2 meters. Okay, so this is work energy theorem. We apply it whenever there is friction, because when there is friction, we cannot use conservation of mechanical energy. So first we solved an exercise where we learned how to calculate W net. Then we solved an exercise where we learned how to apply only work energy theorem. And this last exercise, we learned how we can apply both theorems, mechanical energy, conservation of mechanical energy, and work energy theorem, because in one part of the path there was no friction, and in the second part there was friction. Okay, so this is the lecture for today. But tomorrow we will have a new lecture. Bye bye for now.